In this lesson, we are going to look at the technique of integration called trig substitution. This is a technique that you want to use or may consider using whenever you look at your integrand and you see expressions that look like x squared plus a squared, x squared minus a squared, or a squared minus x squared. Here, x would be the variable that you would be integrating with respect to, and a squared is just a number. So you might see something like x squared plus 16. The way I teach this is a little bit more geometric than the typical calculus book. So I'm going to take you through my steps to set up and solve a trig substitution problem. This involves a lot of geometry, but it involves less memorization than how this material is sometimes taught. So what we're going to do when we work through these examples is we're first going to start with a right triangle. So we're going to pretty much always have the same looking triangle. Then, given what we see in our integrand, we are going to label the sides of our triangle so that if we were to write down, say, the Pythagorean theorem for the right triangle, we would see terms emerging. For example, if we have x squared plus a squared, that looks like a side length squared plus a side length squared equals a hypotenuse squared. Okay, we'll do examples. There is some guidelines you want to follow when you label the sides of your triangle. Typically, one of the sides is going to look like your variable of integration. And what you would like to see is for that variable to appear on what you would call the opposite or hypotenuse relative to the angle theta that we set up. Again, we'll see pictures, so just bear with me for now. Once we've got our right triangle, I like to then just take a moment to write down sine, cosine, and tangent using SOHCAHTOA. And then once we have all of those expressions, we'll start to substitute out terms in our original integrand with new expressions that are going to involve trigonometry. Let's open with this example. We would like to anti-differentiate 1 over the quantity 1 plus x squared. So there in our denominator, we see something plus x squared, and that's what might lead us to think about doing a trig substitution. Now, it's quite possible that you're looking at this and saying, I already know what the antiderivative of that is. It's arctan, and that's exactly what we're going to end up getting. So this is an integral that you might already know, but let's see how we could get to arctan through trig substitution. Okay, so here's the guiding principles. I'm going to start with a right triangle. This we'll call angle theta. And we're going to substitute into this integral expressions with theta. So it's kind of like a u substitution where we switch from x to u. Here we're switching from x to stuff with theta, basically. Okay. Then we have 1 plus x squared. Now, if you think about the Pythagorean theorem, it says this side length squared plus this side length squared is the hypotenuse squared. So the fact that we have a sum of squares here indicates that we might want to label the sides of our triangle with 1 and x, or the square root of this term and the square root of that term. Okay, so I could do 1 and x, or I could do x and 1. Based on the tip I put on our opening slide, when in doubt, if you have a choice to make, you want x to either be on the opposite side or the hypotenuse side. Here, since x is going to be a side length, we want to put it here. So this is the best choice to make for where to put x. Okay, so again, I could have done x and 1, but I like having x opposite rather than adjacent. All right, after labeling the sides of this right triangle with terms that look like the square roots of these added squares, okay, then the hypotenuse has length square root of 1 plus x squared. Notice that's exactly what we see in the denominator in our integrand. All right, so that's my first step, is to sketch a right triangle if I don't already have one, and label the sides and the hypotenuse so that I'm starting to model the terms in my integrand as sides of this right triangle. Then I like to just take a moment and just list out the sine, cosine, and tangent expressions for this angle. You might not use all of them, but I think it gives you like a good next foot to step to so that, if you're like, now what? Just do this and you'll start to recognize expressions from your integrand. Okay, so sine of theta is opposite over hypotenuse. So that's going to be x divided by the square root expression. Cosine of theta is adjacent over hypotenuse, so that's going to be 1 over the square root. Squared? I'm going to write x squared plus 1. I didn't mean to do that, but it's correct. All right. And then tangent of theta is opposite over adjacent. That's why I wanted x over there. So that tangent of theta is just x over 1. You might not use all three expressions in your computation, but typically one of them gives you a nice relationship between x and theta, and in this particular example, it's this third one. So this allows us to say that x is tangent of theta. That's the substitution that we're going to want to make. That also tells us dx is secant squared theta d theta. All right. So where I have dx in my integral, I'm going to replace it with secant squared theta d theta. Let's talk about the quantity 1 over 1 plus x squared. Does that look like anything here? Or maybe after some adjustment, can you rewrite that expression in terms of these trig functions? Here's what I'm going to say, is it looks like the second one, but squared. I could even rewrite this integral one time as 1 over the square root of x squared plus 1. Let me write it correctly this time. So how about 1 over the square root of 1 plus x squared, just so it doesn't look like a weird choice I made. That squared, that returns me back my original integrand dx. Okay. After doing that, this looks like cosine squared. In fact, I'm about to rewrite it as cosine squared, but let me just put it there for a second. This looks like cosine squared, and then dx, I've already solved for down here. This is going to turn into secant squared theta d theta. Like that. So my integral, after switching from variable x to variable theta, I will move it down here to the right, is going to be the indefinite integral of cosine squared of theta times secant squared of theta d theta. Secant squared is 1 over cosine squared, so you take the product of those and you're left with 1. Now let's antidifferentiate that with respect to theta. So the antiderivative of 1 is going to be theta plus a constant of integration. Now we go back to our sine, cosine, tangent relationships that we wrote down, and we want to solve for theta now in terms of one of them. You pick the one that looks the nicest. So I said that x was tangent of theta. That means theta is arctan of x. And you didn't follow what I just did out loud. This is because we said tan of theta of x. That theta was arctan of x. Sometimes you see that written this way. I don't like this, what looks like a -1 power, because it looks like 1 over tangent of x, but this is inverse tangent, so I usually call this arctan. I usually write it as arctan. Okay, so that is how we can get this integral, which we may have already known, but kind of rederive what it should look like using trig substitution. Now in this example, I have t squared minus 16, where t is the variable I'm integrating with respect to. That doesn't look like a side squared plus a side squared. Rather, it looks like hypotenuse squared minus a side squared. So this expression here, you want to think of as like the hypotenuse squared and then minus a side squared. So that's how this expression looks like the Pythagorean theorem. Okay. So let me start labeling the sides of my right triangle. It's going to be the same shape as before. This time I want to put my variable here. So again, you typically want to see it on the opposite or the hypotenuse. So here I see it on the hypotenuse. Then if side squared is 16, one of the sides is length 4. And then the other side is going to be the square root of t squared minus 16 in order to have all three terms satisfy the Pythagorean theorem. Since one of those has the variable in it, I have a slight preference for putting that on the opposite side. Technically, you could set it up the other way around, but I'm going to write that this is t squared minus 16 and this is 4, so that if I then check the Pythagorean theorem on this triangle, it's 16 plus t squared minus 16 is t squared, and that's correct. Okay, so we had our triangle, labeled the sides so that we see something about our sum or difference of squares here modeled on the sides of this triangle. Now let's just pause, kind of relax, and do our SOHCAHTOA. So sine of theta is opposite over hypotenuse. So that's going to look like the square root of t squared minus 16 all over hypotenuse t. Cosine of theta is 4 over t, so that's adjacent over hypotenuse. And then tangent of theta is opposite over adjacent, so we get t squared minus 16 over 4. Okay, so again, that's just kind of my go-to next thing is to write out SOHCAHTOA for the triangle that I've created. Again, usually one of these gives you a really nice way to link your old variable of integration t with the new variable theta, and it's going to be this cosine statement. So in particular, we can now say that t is 4 divided by cosine of theta, that kind of cross multiply. I'm going to write that as 4 secant theta. We like integrating secants and tangents, so here I've got this nice secant theta that's promising. This also tells me that dt is 4 secant tangent. So where I have dt in my original integrand, I'm just going to replace it with this, d theta. Now I want to start looking for what else in my integrand might relate to the expressions here. I have 1 over the square root of t squared minus 16. That looks kind of like this if I flip it. So maybe I will write, let's see, 4 tangent theta is the square root. So this one tells me 1 over 4 tangent theta is 1 over the square root. And now let me rewrite this integral where I'm going to sort of put it in factored form based on the terms I plan on replacing one at a time, and then we'll replace them with their equivalent expressions written with respect to theta. So what I'm going to say here is that this is 1 over t squared, like that, and then 1 over the square root of t squared minus 16, that, and then dt. So I'm going to make 3 substitutions now to rewrite this with respect to theta. I'm going to continue diagonal down to the right. 1 over t squared is 1 over 16 secant squared theta. Okay, so that's the first one. The second one is 1 over 4 tangent theta. That's that one. And then we have dt, which is 4 secant theta, tangent theta, d theta. Okay, so I did 3 terms here and then replaced them one at a time based on how I kind of mapped these expressions to sine, cosine, and tangent relationships from the triangle. It might look bad at first, but it's actually pretty good. The 4s are going to cancel. The tangent's going to cancel. This secant will cancel with one of those. So after all those cancellations, I have 1 over 16 as a constant out front. This all got canceled out, leaving me with 1 over secant. That's kind of a silly thing to write. 1 over secant is cosine. Now I'm ready to antidifferentiate. So we can say that this is 1 over 16 sine of theta plus a constant of integration. And now because we already wrote down sine, cosine, and tangent, when I see sine of theta, I know immediately what to do. So this is going to be the converting it back into an expression with our original variable of integration t. Sine of theta is this. So I'm going to write this as the square root of t squared minus 16 divided by 16t plus our constant. Okay, let's look at this example. This is going to be the third type of sum or difference of squares that we saw on the opening slide. So in particular, we have a constant squared minus our variable squared. So here r is just some fixed number greater than 0. The next step is to draw your right triangle as before, and then figure out how to label the sides and the hypotenuse so that this expression r squared minus x squared looks like some arrangement of the Pythagorean theorem. So if you have a subtraction, then that means the first part has to be the hypotenuse. So my hypotenuse is going to be length r, and then I could put x here or here. Again, the preference, the guideline that I recommend that you follow is to put x on the opposite side whenever you have that choice to make. So if x is here and r is there, then this third side looks like our integrand r squared minus x squared. So that if I then apply the Pythagorean theorem to this right triangle, if I squared the sides, I would have r squared minus x squared plus x squared equals r squared, and that is a true statement. Okay, so next we just do our sine, cosine, tangent ratios. Sine is opposite over hypotenuse, so we have x over r. Cosine is adjacent over hypotenuse, so we have the square root of r squared minus x squared over r. And then tangent is x over that square root expression, so the square root of r squared minus x squared. Next step is to look at the three ratios that you've written down and figure out if one of them gives you a nice way to link x and your new variable theta. It's definitely going to be the sine expression here. So we'll say that x is r sine theta, which means dx is r cosine theta d theta. So where I have dx in my original integral, I'm going to replace it with this new expression, r cosine theta d theta. Everything up to this point is kind of routine for me. Draw the triangle, label the sides, do the SOHCAHTOA, figure out the best, cleanest looking relationship between x and theta that you've written down. Then you get a little creative where you start trying to make replacements in your integrand with these expressions. So what I actually have in my integrand is the square root of r squared minus x squared. And then you're like, okay, well, does that look like any of these? Not exactly, but if I took this cosine statement and multiply both sides by r, then I could say that the square root of r squared minus x squared is r cosine theta. So let me work this out over here. This integral is going to be the square root of r squared minus x squared, but I'm going to solve for that in terms of theta as r cosine theta. Then dx is going to be r cosine theta d theta. Like that. Since this is a definite integral, when we switch from x to theta, we also want to update our bounds. It's just like in u substitution. When you do u substitution with a definite integral, you switch your bounds from bounds on x to bounds on u. Here we're going to switch them from bounds on x to bounds on theta. We haven't done this yet, which means I also haven't talked about the right domain for theta based on the trig relationship that you use to define x. Let me do that now for this example. So we have x equals r sine theta. If I'm going to update my bounds, then I would like to figure out the right theta to correspond to when x equals 0 and when x equals r. So the question is, if x is 0 for the lower bound, what should theta be? And for the upper bound, when x is r, what should theta be? In other words, what should theta be to have sine theta equal to 0 versus sine theta equal to 1? For any trig relationship that you create relating x and theta, there's a correct domain for theta. For an indefinite integral, typically don't worry about it. I didn't worry about it in the last two examples and everything checked out fine. But when you have a definite integral, you need to make a choice here. If you look at, say, the unit circle, my sine values go from -1 to 1. So I want to pick one kind of vertical branch of this circle, and what you want to choose is the right side. So for a sine relationship defining the relationship between x and theta, we'll say negative pi over 2 is less than or equal to theta is less than or equal to pi over 2. I'll summarize these for the other trig functions in a few minutes, but let's just work with sine for now. So this is going to be the domain for the sine function, so that we're looking, or sorry, this is going to be the domain for theta, so that when we look at our sine values, they take us from -1 to 1 in a way which is not redundant. So we go from -1 to 1 and then we stop. So given this domain for theta, what would be the right choice for theta in order to have sine of theta equal to 0? It would just be 0. It would be this one here. On the other hand, if I went sine theta all the way up here at 1, I'm going to take theta equal to pi over 2. All right, so the new bounds for my new variable theta go from 0 to pi over 2. Okay, and again, I will restate what theta values you're looking for in general later. So if you'd like to see this again, we will circle back around to this. Okay, let me keep going, and I hope I have enough room to do this. I'm going to do a power reducing formula all in the next step. So let me pull the constant r squared in front, and now we're integrating from 0 to pi over 2. Cosine squared with the half, or the power reducing formula, is 1/2 times 1 plus cosine 2 theta. Like that. We are now ready to anti-differentiate. See if I can squeeze it in the remaining space. Let me write actually r squared over 2. We'll pull that 1/2 out front. That leaves us needing to anti-differentiate 1 plus cosine 2 theta. The antiderivative of 1 with respect to theta is theta. And then the antiderivative of cosine 2 theta with respect to theta is 1/2 sine of 2 theta. And then this is a definite integral with lower and upper bounds that look like 0 and pi over 2. Okay. Let's plug them in now, and I think I will go ahead and erase this picture I drew here so that we can finish this. Okay. So we'll have a leading coefficient of r squared over 2, and then I'm going to say theta over 2 plus 1/2 of sine of twice pi over 2. But that is sine of pi, and that is 0. Then plug in 0 for theta, and you get 0. 0 for theta here, you get sine of 0, which is 0. So everything else is 0 in there. That leaves us with, oh, this was 0. Okay, so that leaves us with pi r squared over 4. Pi r squared over 4. You think, hey, that sounds familiar. That's because it's a quarter of the area of a circle of radius r, and that's actually what this integral was really asking for us to compute. So if you graph the function y equals the square root of r squared minus x squared, it's going to be the upper semicircle of radius r. Okay, so that is the graph of y equals the square root of r squared minus x squared. We were asked to compute the area under the graph of this function over the x-axis from x equals 0 to x equals r. So in particular, we were looking for this area in the first quadrant. So that's like saying, what's the area of 1/4 of a disk of radius capital R? And that's going to be pi r squared divided by 4. In this example, we have a subtraction of perfect squares. So we are going to be looking to put one of those on the hypotenuse and the other on the leg. We'll make a little choice there. So notice 4x squared is 2x squared, and then minus 9, which is 3 squared. Since this is the leading term in a subtraction of squares, we want to put that on the hypotenuse. So the hypotenuse of our right triangle is going to have length 2x. Then I could put 3 here or here. My preference is going to be to put 3 on the adjacent side so that the remaining side, which is going to pick up an x term, is the opposite. So, if you have a choice to make when labeling your sides, put anything with a variable on the opposite side. So this is going to be 4x squared minus 9. Just leads usually to better trig. There is a choice you could make here, but usually the trig is better when you put this on the opposite side. Let's see what that trig looks like. So we've got sine, cosine, tangent. Sine is going to be the square root of 4x squared minus 9 over hypotenuse of 2x. Cosine is going to be 3 over 2x. And then tangent is going to be the square root over 3. As usual, one of them gives us a really nice way to link x and theta. So in particular, let's say x is 3/2 secant theta. That means that the dx differential in our starting integrand can get replaced with 3/2 secant theta tangent theta. Okay, let me pause here for just a minute. We know how we're going to replace dx, but how are we going to replace 1 over 4x squared minus 9 to the 3/2 power? So that's like the square root cubed. So work out what trig might be relevant there, and then I will come back and finish this computation. Okay, to replace that term in our integrand, I would like to just see the square root expression. I could then cube it, or first I could flip it and then cube it to make it look exactly like the integrand. So if I multiply over by 3, like that, we know that 3 tangent of theta is the square root. So let me write this as 1 over the square root of 4x squared minus 9 cubed. That's equivalent to the original integrand, then dx. We can now say that, continue to the right if I can, that 1 over the square root is 1 over 3 tangent of theta, and then cube that. Tangent of theta, and then I'm going to cube the whole thing. Okay, so that switches that term into theta, and then dx will get replaced with 3/2 secant theta, tangent theta, d theta. Okay, let's now bring the constant out, cube it here, so 3/2 times the indefinite integral of 1 over 27 tangent cubed theta, secant theta, tangent theta. So the 27 will come out, the 1 over 27, and then this tangent theta can simplify our denominator, so that will be tangent squared. I'm going to end up with secant over tangent squared. You might be able to figure that out in terms of secant and tangent, but I'm just going to be more comfortable at this point if I switch it to sines and cosines because I know those functions really well. So let's see, if I pull 27 out, that simplifies with the 3 to 1 over 2 times 9, so 1 over 18. Secant theta is 1 over cosine. Tangent theta is sine over cosine. So 1 over tangent theta is cosine over sine. In other words, this is cotangent. So we'll have cosine squared theta over sine squared theta. Okay, so this is equivalent. I just like this form better. Now, again, we have some cancellation, like that. And that leaves us really with a u sub. If u is sine theta, du is cosine theta d theta. So this is a nice clean u substitution. So we will let u equal sine of theta du will be cosine theta d theta. That leaves us with 1 over 18 times the antiderivative of 1 over u squared du. I'm going to write u to the negative 2 power du. Okay, so at this point, we switch from x to theta, and now theta to u. So we've done 2 substitutions in this problem, and sometimes that happens. Okay, let's keep going all the way to the end. If I anti-differentiate u to the negative 2, it's negative u to the negative 1. That's the power rule going in that direction. So I will write negative 18, negative 1 over 18, times 1 over u, but u is sine theta. So 1 over sine theta plus c. I hope I didn't do too much there at once. Okay. But the antiderivative of this is negative 1 over u, so that's negative 1 over sine theta. And now I converted from u back to theta. In the process of doing that antiderivative, we still have to convert all the way back to x. So what is 1 over sine theta? It's the reciprocal of this expression, so it's hypotenuse over opposite. So that tells us that the final answer is going to be negative 1 over 18 times the reciprocal of this, so that's going to be 2x over the square root of 4x squared minus 9. That's our constant of integration. Okay, so for me, there were 2 levels of substitution in this problem, but that's okay. Just make sure your final answer in an indefinite integral like this is written in terms of the starting variable x.